back to what Sean mentioned, it's, we know what the limitations are of the current materials that we use, and whether it's concrete or steel, pre-stressed concrete, there's obviously finite service lives associated with these materials. And so one of the greatest advantages of the advanced composite materials is getting the extended service lives. So, having been a bridge engineer for almost 4 decades now, that's what kind of inspired me to come up with the HCB. And here's a shot of just a typical beam before it's shipped out of the factory, and you can see some of the components of it. The strands at the end are just the lifting loops. You can see the galvanized reinforcing steel that functions as the shear connectors. I'll talk more about that. And the rest of the bridge is basically a composite shell. So if we look at basically the components of this structure and the concept of an HCB, it's to develop a structural member using several different building materials and using each material in its most cost-effective application. So what I mean by that is, if you look at the sketch on the right, there's a concrete compression arch, there's a steel tension tie along the bottom, there's a fiber reinforced polymer shell, and then there's the steel shear connectors that allow that beam to act compositely with the concrete deck that's then placed on top of it. So again, we know concrete functions very well in compression. We know steel functions very well in tension, and I always refer to as the human endoskeleton, where our bones take the compression, our ligaments and tendons take the tension forces, and then our skin provides this elastic containment that keeps everything together and helps transfer the shear forces. Just a brief overview of this particular type of composite. We use what's called a balanced quad knit fabric. That means you've got a fabric that's got multiple layers of unidirectional glass in 4 different directions. So we've got longitudinal, transverse, and then plus minus 45 that gives us our shear capacity, and then usually just a continuous strand mat that gives us some stability. It's infused in a epoxy vinyl ester resin or epoxy or polyester resins, and that what results is really a fiber reinforced polymer material that gives us quasi-isotropic behavior. So we're basically getting the same material properties in every different direction with the balanced fabrics. For the steel, we typically use just galvanized post-tensioning strand, 1860 MPa, same stuff you would put in a pre-stressed beam, but we typically use galvanizing just for the extra corrosion protection. What the benefit of this is, we can cut it to length, any length we want. We put a 90-degree bend at both ends. We lay it in the mold, and the strands are developed in the end of the beam to catch the thrust of the arch, and then it's basically infused in the same laminate as the FRP. So it's really a steel and glass reinforced laminate when we're complete. Here you can see the manufacturing process. They just throw everything in a closed mold, lay in the glass, the steel, the foam. The foam core comprises the volume, the interior volume that doesn't contain the arch. Pull vacuum on it, infuse the resin in, takes about a half an hour. You can build a beam a day in each mold. Then you see on the right there, just setting the composite lid on top of it to get the final roadway, or not the roadway surface, but basically a stay-in-place deck form. The concrete we use is nothing special, just a 41 MPa self-consolidating concrete that overdosed with super plasticizers and viscosity modifiers, so it flows out like water. And I'll show you a little bit more about how we fill this later, but with the SEC, you do a J-ring test instead of a slump test, because you basically want it to be able to flow through the beams and fill all the voids. So the benefits of this technology, obviously you get the lighter weight, so you've got reduced foundation costs. It's usually the mass of an HCB is about the same as a steel beam when they're all said and done. It's about 1/3 of what a concrete beam is. Empty, it's about 1/10 what a concrete beam is. Reduced carbon footprint. Again, cement production is the worst contributor to greenhouse gases in the world. Something like 3.2% of all carbon is produced through cement manufacturing. We're optimizing each material. Like I said, we're just using the minimum amount for each component. Greater corrosion resistance gives us a more sustainable structure with less maintenance costs. It's actually simple to design, fabricate, and erect, and hopefully when I get done, you'll believe me. And ultimately, we just want to provide the public with safer bridges. And lastly, reducing the burden of infrastructure costs on future generations through the better performance of these materials.